Hi, these are just some quick comments about the Landsat program. Excuse me. About the Landsat program here in Geography 243 Remote Sensing. The Landsat program, as we know, and as we've begun working in remote sensing, everything that we're working with really falls somewhere on the electromagnetic spectrum. Again, this is just a reminder for you. So Landsat coverage, this is a bit dated diagram, but it starts in 1972, the launch of Landsat 1. Landsats 1 through 3 take us pretty much through the 70s and into the 80s. Lower resolution, both spatially and spectrally, than the satellites that we're currently using. Starting with Landsat 4 in 1982, I believe, and then Landsat 4 and 5 with the thematic mapper became the operational sensor for the last 20 years of the 20th century in terms of the high resolution multispectral imagery, or medium resolution, I guess you would say. 30 meter is not necessarily high resolution. Up through the present day. Landsat 6 failed to achieve orbit. Landsat 7 worked fairly well for about 3 or 4 years, launched in 1999, lasted through into 2003, and then there were some system failures on there that really made the thematic mapper much less usable and less valuable. So fortunately, Landsat 5 lasted until really the launch of Landsat 8 and the initiation of the operational land imaging system, the OLI system, and the thermal infrared sensor on Landsat 8. So again, this is an incredibly valuable set of data if you're interested in monitoring changes that have taken place on Earth and what's actually happening and has happened on Earth starting in 1972. So it really is there's nothing really to compare it to in terms of environmental, land cover, oceanic analysis data sets that we have available to us. So again, this is another look at some of the characteristics of Landsat, early Landsats, Landsat 1, 2, 3 in particular. 4 and 5 also had the same instruments on it and weren't used very much because of the thematic mapper, which was a higher quality instrument starting on Landsat 4. Here's Landsat 7 and then Landsat 8. Again, we can layer that on here, and really this is a diagram that needs to be updated to include that, and we actually do have a diagram I can show you that does include Landsat 8 in comparison to Landsat 7. And then here are some of the characteristics of some French satellites that were launched beginning in the mid-1980s that really were very close to in some ways close to what Landsat has accomplished, although certainly the imagery is not available to us in the way that it is, the way that Landsat imagery is being in the public domain. So in this diagram you have spatial resolution in meters on the vertical axis and spectral resolution along the wavelength across the visible, the near and mid infrared, and then all the way up into the thermal infrared. So it's a nice sort of shorthand diagram for looking at this. And then the Landsat TM 4 and 5 band resolutions 1, 2, 3, 4, 5, and 6, and you can see lower resolution on the thermal. We're now up to 60 and I believe even 30 meter resolution on the thermal with the Landsat 8, launch of Landsat 8. And then this diagram here shows you a bit of the curve of energy that is available, electromagnetic radiation that's available with the occlusions, or the places where the atmosphere shuts down because of absorption and scattering. And it shows you the spectral range of the various Landsat TM sensors. This is the ETM, but again, virtually identical to Landsat 4 and 5 thematic mapper data. And then here are the channels for Landsat 8, what was called the LCDM, and now called Landsat 8. Again, these are this is a useful shorthand for us as we start to work with these data and do some things with it. The orbital parameters of Landsat are pretty interesting. We have over every 16 days the satellite returns to the same location that it was at previously. These locations are actually called paths and rows, or path rows, and so the a particular scene has a designation, a shorthand that you can use when you're searching for that scene. It's something you may want to get familiar with, particularly in areas where you have a particular interest, and it allows you to do quicker searches. You can see, the width of it is around 185 kilometers every 16 days. It's relatively not necessarily very low Earth orbit. It's a little bit higher than that. The data that we work with, by the time we get it, is 8-bit data. So, you have a range of integer values from 0 to 255. And the data storage is, it varies through the history of the program. So you can kind of read off a history of magnetic data storage from the Landsat program up to the present time, where now we're pretty much sending everything up to geostationary satellites and then down for near real-time access to Landsat data. So again, this diagram just gives you a sense of how the pathing works. So on day 1, and then there would be the next pass would be right here. So it's like you could take this whole swath. This is a 16-day swath, and shift it to the right every orbit, right? So on day 2, you get the idea when you look at this. This gives you some sense, though. So as the satellites come over the pole and they're on their descending mode, flying in sun synchronous mode, the next time that they come around, this is how far the Earth has turned under that satellite as it passes right down the western U.S. in this diagram. This is kind of a dated diagram, but it really is a story of the 70s and even into the 80s. These are the ranges, the coverages of ground receiving stations, various ground receiving stations that were operating during the 1970s and the 80s. And so the satellite, by and large, was only able to collect data when it was in range of ground receiving stations. The other options that it had were not very successful, I guess you would say, in terms of recording data on board the satellite and then broadcasting it or transferring it into a ground receiving station when it was in range. So you can see these holes in the coverage: Tierra del Fuego, Central Africa. There's a large area in Central former Soviet Union. So we didn't have great coverage, and also, it should be said, New Zealand also sort of left out, and many of the islands of the Pacific outside of the range of those ground receiving stations. So very spotty coverage during the 1970s, principally with the MSS, multispectral scanner sensor, lower resolution. So again, this is just gives you a sense for how these data may look. This is a topographic map of the junction of the Little Colorado River with the Colorado River out in the Four Corners area of the United States. Here's a little closer look at this, just to give you a sense for the detail in the Geological Survey topographic maps. and the high terrain that we're looking at here, the high, really steep cliffs. This is canyon land, right? And so here's the Little Colorado and the Colorado, and this is in channel 1, which is the visible blue, and you can see the Colorado, or the Little Colorado, looks quite reflective, and the Colorado is fairly dark, even in the blue. It's fairly clear. And so here's a histogram of that same image with about 250,000 pixels, I think, in that image. And so you get pixel counts in the histogram, all the way across the 8-bit range from 0 up to 255. And so here's channel 1 in that fashion. Here's channel 4, and again you can see there's quite a bit of change here in the way that this appears. And this has to do with reflective. This is reflective infrared, channel 4 thematic mapper data from 0.75 to 0.9 micrometers wavelength. So just outside of the visible, and here's a histogram of these data, at least partial histogram of these data. Here's channel 7, again in the mid-infrared, again very somewhat similar to the channel 4 data, but a bit different. And here's a histogram of these data, again partial histogram of these data. And then sometimes we look at data as in relation to one another. So in essence what we're looking at here is a scatter plot. On the x-axis is channel 1, and on the y-axis is channel 4. So we're looking at visible correlated with infrared, and you can see it is quite linear, and the r² is around 77.9. Okay, so there's the interpretation of that is that 77.9% of the variance in one of these channels can be explained, or you might say is redundant, with the variance in another channel here. So that it's highly linear, and you might say correlated, right? Again, here's another correlation. This between two IR channels, and you can see the r² is quite a bit higher. It's 92.6. So again, 92.6% of the variance from one channel is explained or certainly accounted for within the other channel. Highly linear, highly correlated, and you might say highly redundant visually, right? So Landsat